Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we are happy to have Dirk Bergman from Yale. This is the second part of a two-part talk. Stephen Morris was here a few months ago, so if you were not at Stephen Morris's talk, then you are going to have incomplete information, but it's okay. Because the talk is about robust predictions in games with incomplete information, and we're very happy to have Dirk here.
Great, thank you. Is that it's okay? I get the microphone, but I don't want to be too loud for you. So, okay.
Can't be too loud here.
We'll see. Excellent. So this is indeed a joint work with Stephen, and who also told me that I should expect a very nice CD afterwards from my presentation. But he was suggesting that perhaps besides a CD, we could also get a transcript of the talk, so that now that we have such nice slides, we probably also have a nice paper afterwards with a transcript. So I don't know whether that's in the budget or not. In any case, this is sort of continued work with Stephen on sort of the robustness of our understanding of game theoretic setting. And in earlier work, and the work that Stephen initially presented maybe in December, he very much talked about just mechanism design, that is, situations when we can design a game such that it has favorable properties. Today we want to sort of step away from that and just look at general game theoretic environments and see how much we can say about the outcome of games, that is, how much we can say in terms of predictions, when we as an analyst or as an outsider have only limited information about the information that the agents actually have access to. We will take a fairly general view of the problem. I will give you some general results initially, and then in the second part of the talk you will see that I'm going to sort of narrow the focus a little bit in terms of the environment that I'm looking at and the specification, to give you a little bit of a sense of the direction and the sharpness of the result that we may obtain by using this approach. Okay. So the general part of this is that indeed in many economic environments, and in particular in games, there's an important aspect of our coordination, that is, an agent's action, what he should choose, will depend on what his expectation and what his beliefs about the underlying fundamental of the environment is. But it might also depend, and typically will depend, on his expectations about other agents' actions. Okay? And that's what I mean by coordinations motif, that is, I have an interest or knowing, or at least forming an expectation about what the likely action of the other agents is. And to the extent that I try to predict as an agent what the other agents are doing, I'm also interested not only in their beliefs about the fundamental variable, but I'm also interested in the beliefs that the agents have about their actions and so on. So that is, we want to speak not only about beliefs in terms of what we predict about the value of the underlying fundamental variable, but we also want to speak about higher order beliefs, namely beliefs about beliefs. Okay? But in economics, in economic environments, in games, typically it is the case that the analyst will have actually very limited information about what these higher order beliefs are. Okay. It will be very difficult to elicit that information. It is almost impossible to actually observe it, to reveal preference arguments. So from an outsider to make very strong assumptions, hypotheses about what these higher order beliefs are might be very difficult. And so what we would like to do is to say, what can we say about the outcome of the game? What can we do in terms of the prediction, even if we know or we assume very little about the structure of the beliefs, and in particular about the structure of the higher order beliefs. And we would like to know what kind of predictions can we make if we robust predictions, that is, predictions which are not dependent on the exact specification of the beliefs. Okay. And in this talk and in the paper, we focus on two sides of the problem. Namely, one is the prediction problem. That is, we want to ask what, on the basis of the assumed observable, on the assumed structural characteristics, can we say about the observed and endogenous statistics of the game. That is, what are the actions or the correlation between actions and states. Okay, and then we also may want to ask the reverse question, namely the question of identification. That is, given the observed outcomes, given the actions, what is it what we can learn or what we can infer about the underlying parameters of the model that we think characterizes a decision problem in which the agents find themselves. Okay. And to the extent that we make weaker assumptions about the structural properties, of course, our predictions may get weaker. And the reverse is also true. That is, if we have weaker assumptions on in which world these agents are living, then it will be also the case that the identification problem will be harder. Okay, so instead of being interested in point identification, where we're trying to exactly infer the structural parameters, we then might ask, can we at least come up with partial identification or with set identification? And that is sort of the basic problem. Okay, to maybe just recap a little bit of where we stood when we just analyzed mechanisms. In mechanisms, we actually have considerable leeway of designing the games and designing the game in such a way that it's actually has desirable properties in the sense that it may be insensitive to the private information that the agents are having. Okay. And so in earlier work with Stephen, we asked sort of two classes of questions. So the first question was, let's say we have a given social choice problem. Let's say we want to say implement the efficient allocation. Think about giving an auction, in an auction, given the object to the person with the highest valuation. That's sort of the social choice problem that we're interested in. The first question is that we could ask, is it the case that we can solve that problem? That is, make it incentive compatible for everybody to reveal us their information. And can we do that irrespective of what the information is that the agents may have access to? Okay. And in the first paper, we showed that we can do that if and only if it is the case that the underlying social choice problem has a strong stability property, namely it's post-incentive compatible. Okay. And since we're interested in sort of predicting outcomes, we could then strengthen this original question and say, can we make sure that not only there exists one desirable outcome, but can we make sure that in fact all outcomes of the game are desirable in the sense that they correspond to what the social choice function is. That's sort of the famous implementation problem as posed by Maskin originally. And here we show that, yes, indeed, we can even solve that problem robustly, provided that the preferences are not too strongly interdependent. And what that is basically leading us to is sort of a contraction-like argument, which shows that eventually we will be able to reveal the information truthfully, no matter what the information of the agent is.
So, in particular, then, the only if part, you are actually showing that if they are too interdependent, then you've got counterexamples?
Then whenever they are too interdependent, then it will be the case that there will be belief structures or information structures when it will be impossible to get to the efficient allocation. So that it's this sharp characterization which makes this sort of a more dramatic insight, and which gives it a little bit more humph, as it were. Okay. All right. Good. And so today we will not have in some sense the strengths of designing the game, but we rather want to fix the game and then simply say, can we get at least some prediction, can we make maybe some set prediction of what the likely outcome is? Okay. And we're going to take sort of a route somewhere in between the typical economics approach to equilibrium, which is sort of looking at Bayes-Nash equilibrium, and a route which is often favored by computer scientists, which typically look at dominant strategy implementation or worst case analysis, where we are going to ignore all possible priors. That is where we're basically trying to make a prediction irrespective of the information that is prior free or detail free or distribution free, whatever that characteristics might be. Okay. And the precise distinction that we want to make today is that we want to assume that the agents share a common prior over the payoff relevant aspect of the game, that is, say, about the fundamental underlying variable, okay, and that information is also known to the outsider, to the analyst. But what the analyst is not knowing, does not know what is the strategic information, what are beliefs and the higher order beliefs that the agents have access to. So it's this distinction that we want to make, and then we want to say, can we make predictions about the nature of the game irrespective of the specific beliefs that the agent have while playing the game? Okay?
So who's the analyst?
The analyst is sort of the outsider who wants to make a prediction about what the outcomes in this game is. That is, he will know, and it will be true that the agents will share a common prior, okay, but he will not know what that common prior is.
So should I think of?
So we're going to make we're going to make the first distinction is that the principal will not, so the outsider will not know what the strategic information is. But what we're going to allow is that, what we're going to assume is that whatever that strategic information is, the agents will have a common prior over their information or their type space, as it were. Okay, so they will share a common prior. They will, of course, have then access to private information, but there will be a common prior. Okay, thank you, Sandeep. And I will give you an example to make clear what that distinction will amount to.
In practice, the analyst is the FCC or something like that?
Think about the FCC who would like to say, we're going to sell the spectrum with this auction. We can't be quite sure what the information is which the agents have, the bidders have access to. But what we'd like to say is that no matter what the information is, no matter what the strategic information is that the agents have access to, the range of the outcomes is going to be in this area or in this set.
Well, but then the FCC is a player because they sell the spectrum and want to make money or not money from it. So I'm going to suggest a game, okay? And for this game now, I want to say I'm not sure what the information is that the agents will have access to. In particular, I'm not sure how much bidder 1 knows about the valuation of bidder 2. As I'm contemplating this game, what I would like to know is what is the range of outcomes that could occur in this game. Okay? And what I guess you're pointing now to is that I could now ask a second question. If I'm now allowed to basically change the rules of the games, I might say in some games I get a higher guarantee, say in some games I get a lower guarantee, and that is something we maybe have a little bit of time to talk about in the end when we say, well, what does that lead us to in terms of suggesting robust policies, that is policies which are good across a wide spectrum of a wide array of information structures. Okay? I see. It could also be that the FCC is not even interested in selling something, but maybe wants to just overlook something and want to get some idea maybe whether they allow a merger or not, what it will do to the market. And they are sort of the outsider analyst who doesn't really, I mean, he has some sort of
oversight. But he would like to know what are the range of outcomes that could occur if he, say, were to allow for a merger in this market. That's a good way of paraphrasing, also giving an example. But in general, the example of the auction is sort of irrelevant that you may want to keep in mind. To simply think about as the payoff environment, simply the valuation or distribution of a valuation. What I refer to as belief and higher order belief is basically the strategic information this bidder 1 has about bidder 2, about bidder 3, in terms of what their valuation, what their beliefs are, and so on. Okay? Okay. And so we will give sort of a general description of our approach, and then we will narrow it down, and we'll look at the class, or basically at the class of quadratic games. That's going to be our payoff environment, where the underlying fundamental is going to be normally distributed. Okay? And then we're going to say what can we make and say in terms of robust predictions about the outcome of the game. Okay? In the case when we have quadratic payoffs, a normal distributed underlying variable, then of course one interesting aspect is that basically at least the Bayesian equilibrium outcomes are completely described by the mean action that every agent is taking and by the variance covariance matrix. Okay, so essentially we have sort of a nice object to work with where prediction of an equilibrium is in some sense just the prediction of the first and second moment, and when we come to set predictions, we basically just have moment restrictions of what this distribution can look like.
So So what this, I mean, it's kind of surprising in a way, right? That the third order doesn't come into it at all. I mean, it's kind of.
That comes in from the fact that with quadratic games, the payoffs, all the interaction.
This is quadratic games.
So
Yes.
Absolutely, you're absolutely right. Otherwise, it wouldn't work.
But otherwise.
Right? And but of course,
Yes.
another way to then think about this is just basically sort of a local analysis where we do. Okay. Okay. So the results.
Implicit function kind of.
Exactly.
Right. Like
That's right.
contraction mapping in an implicit function. Okay.
Right? But since we're just looking at quadratic games, our local arguments will be perfect global arguments. Yeah. Okay. So what I'm going to now then do today is to basically give you first a general epistemic result, which says rather than analyzing the Bayesian Nash equilibrium for every possible information structure, I'm going to show that that's equivalent to just analyzing what we call the Bayes correlated equilibrium, which is basically the correlated equilibrium a la Aumann, but in an incomplete information setting. Okay? That is, there will be an exact equivalence between all possible Bayes Nash equilibrium and the set of correlated equilibria. Okay, and I will use that equivalence and to just characterize the Bayes correlated equilibrium, and that would give me a very sharp characterization of what the outcomes in the games are. Okay, and then I will use that insight in the class of quadratic games. Okay, so the setting now to get a little bit formal, we're going to look at a finite or infinite players setting. Typically, when we go to the quadratic game, we'll just look at continuum of players. There's an individual action by agent I, which is small a, and there's an action profile, which is simply the list of all the actions. There's a payoff relevant state, payoff relevant because it enters into the utility function of the agents, next to, of course, the action of the agents. Okay, and I want to think just about this vector of utility profiles as a function of the action and the state as a belief-free game. Okay, it's belief-free because at that point we have not yet said what is it what we think about the likelihood of state theta, or what is it what we believe about the information that the agent have access to. Okay.
So wait, what is the U?
The U is simply the vector of utility profiles of all the agents.
It's on A cross.
Right? And the payoff function just depends on the actions.
Right, he missed that one.
I just didn't make the connection. Good, yeah.
Yes. Okay, so that's basically the payoff environment. And then the aspect that we're going to add to that is we're going to specify a prior distribution, a common prior psi, over the payoff relevant variable. So that is the common prior over the fundamentals, and that we assume is common prior among the agents. Okay? But beyond that, we're not going to specify what the beliefs of the players are about the knowledge that they have and their higher order beliefs. Okay? Okay. So essentially what we have now is just the description of the actions available and the distribution of the states. Okay, and the notion, the equilibrium notion that we're going to be interested in, is the notion of Bayes correlated and Bayesian Nash. So let me, at this point already, start out with the notion of a Bayes correlated equilibrium. What do we mean by Bayes correlated equilibrium? We simply mean that there exists a distribution mu, a joint distribution over the actions that the agent taking and the state. Okay, and we call such a joint distribution a correlated equilibrium, or Bayes correlated equilibrium, because there's still uncertainty about the underlying state of the world theta. If it's the case that whenever we recommend that agent I takes action AI, and he's forming the expectation of what the other agents is doing by means of using the joint distribution mu, then he will find that action preferable to any other action he could also take. Okay.
So we assume that he looks at the world and forgets his own probability distribution.
And forgets his
own part in the probability distribution.
No, but he can condition on the fact that he's going to take an action AI. So it's
right. But there is a probability distribution about the actions of the
others, which is precisely this joint distribution mu. So we're going to say let's
from a distribution mu of the, which is just a general joint distribution.
Just a general joint distribution. We call this distribution. Pardon me.
So So I don't condition on me, I leave me out of what.
No, the joint distribution gives me a joint distribution about my action, my opponent's action, and the state. I call that a correlated equilibrium distribution if it has the additional property over being just a joint distribution that whenever I'm basically taking the draw of taking the action AI, I can condition on that aspect, namely that I'm supposed to take the action AI, and then I find that better in terms of the expected value that is accruing to me than taking any other action
He's integrating
AI
for
prime.
everybody else's action
And he's
all the
integrating.
payoffs.
But
Exactly.
I understand that. The question I have is, do I just then look at one particular action of myself, or do I condition on me and afterwards
I condition on me and my act. No,
me?
I condition on me and my action, and this must be true for every possible action that I'm taking. Right? So it's sort of an interim evaluation. For some reason, I'm arrived today with the idea that I should play AI, and given that this is the joint distribution, I'll find it in my best interest to follow that.
But AI is given by chance.
By chance, exactly. And simply because I know what the joint distribution is, that should alone give me enough information that it thinks that I think it's a great idea for me to pursue AI rather than pursue any other action AI prime.
But I don't understand that, because AI is also some outcome which is probabilistic.
Yes.
You give me some AI. You
So,
might as
so,
well
so
give
think
me
about
a
this.
different
So
AI.
think about this as basically a joint distribution, and we're going to get a random sample, which is the A, okay, and then every agent is just being told the action AI that he's supposed to take. If he's told to take action AI, he says, well, because we have this joint distribution, I'll find it my interest to do that, conditional on the information that gives me about the action of the others to pursue that rather than something else.
But that means, since, let's say, the distribution would have complete support,
Yes?
I could get any possible AI, so that
Yes.
means
That means there
any
must be
possible
something
AI has to be in equilibrium. So no matter what I play, should be
But
equilibrium.
notice that there can be some correlation, that's the whole point, there can be some correlation between the AI I'm supposed to take and the AJ somebody else is supposed to take. So it's a correlation. It's the fact that I'm asked to choose AI, which then gives me some information. I don't know exactly what kind of information, but if it's a correlated equilibrium distribution, it must be the case that this information alone is enough to give me incentive to choose AI. Well, and maybe it's going to be easier if we sort of go now to the base Nash equilibrium, then establish the relationship. Yeah? But if for the moment I just have gotten your interest, then that's great. Okay.
You
Okay.
have Christian's interest, and he just drove everybody else away, but it's okay.
So far, nobody has left. Okay. Okay. And of course, the important assumption is that this joint distribution preserves, once we take the integral over the action, preserves the property that it coincides with the prior distribution over the payoff states. Okay. Good. More typically, how would we have defined a Bayesian game? We would have said, well, every agent will get some kind of information, okay, and that information would basically induce a conditional probability system. That is, given the true state of the world, I would give every agent some kind of signal, a noisy information about what the true state of the world is. That is, a probability distribution over possible signals, okay, and then I would define a standard Bayesian game as simply as this triple of the utility function, the prior distribution, and the information structure that the agents have access to. Okay? We'll come back to that relation in a second. And when I've been given the information Ti, then I will have had to make a choice about what my proper action is. Okay? And the notion of a Bayes-Nash equilibrium is now the notion that given my information Ti, I have to choose an action, and that action in expectation ought to be better than what I could do in terms of any other possible action. Okay? So perhaps now you see sort of the conditioning a little bit clearer in the sense that I'm taking the expectation now over the type space, over the fundamental, that is theta, and I also take the expectation over the type of the other agents. Okay? And because the type profile or the signal profile T was generated randomly, according to some known law, given the state of the world theta, I can now make an inference from my own observation of Ti about what the other agents have observed and also what the underlying state of the world is. Okay? And that is sort of the classical formulation of a game of incomplete information as suggested by Hazani, Mertens, and Samir, where we simply say the way we represent incomplete information is that every agent has some piece of information. Let me just complete this thought. And that information is the type of the agent, small ti. Okay? If you have a common prior distribution, which is what we're going to assume today, then there is going to be some fixed distribution over the entire type space. Okay? And the important part of that is that my own type Ti then basically gives me two pieces of information. It gives me a piece of information about what is the likely type of the other agent. That is, this is now my belief about the type of the other agent. And because the type of the other agent also is being generated by a particular state of the world, it will also give me some information about what the true underlying state of the world is. Okay? And when we define the notion of a correlated equilibrium, then the strange thing on which Christian seemed to have picked up is that it didn't specify any information in terms of a type, in terms of a conditioning event. It seemed very much to be a reduced form approach. Okay? Because we didn't specify a type space. We didn't specify specifically what's the conditioning that occurs. Okay? And the interesting result, the first interesting result that we're going to present is that that reduced form is in some sense exactly the right reduction. That is, every information structure of that form, every conditional probability system of that form will lead to a base Nash equilibrium. Okay? And the set of all the base Nash equilibrium are basically the set of correlated equilibria. Okay? So let me say that slowly. That is, let's start out with a particular information system. Let's start out with a particular base Nash equilibrium. Okay? Then I could be interested in knowing what is the induced distribution over actions and underlying states of the world theta that is being generated by that information structure. Okay? And that equilibrium. Okay? These two objects, namely the equilibrium and information structure, will give me a joint distribution over A and theta. Okay? And I could call this mu as a function of the equilibrium sigma simply as the Bayesian Nash equilibrium distribution over actions and state. Okay? And for every information structure, there could be a different equilibria, and for every information structure, there could in fact be multiple equilibria. We don't know that. Okay? But the thing which is going to be important for our purpose here is that there is a fundamental equivalence between these two notions. That is, we can show that a joint distribution just over actions and the underlying states theta is a base correlated equilibrium if and only if it's a base Nash equilibrium for some information structure. Okay?
Because I just thought, when I asked this question, I thought that seems a very strong condition, and now I see that it is actually what kind of strong condition it is.
That's right. So that's sort of, and then, but it's sort of a closure condition if you want to think about this. Is whatever base Nash equilibrium I can generate, whatever information structure it is, it must be also a correlated equilibrium distribution. And if I think about the set of all correlated equilibrium distributions, these are precisely and exhaust the possibilities of all Bayesian Nash equilibrium. Okay? So rather than to say and pursue what is the specific base Nash equilibrium and a specific information structure, I'm just going to take an agnostic view on the base Nash part, and I'm simply going to say, well, I might as well just look at the set of correlated equilibria, which has the advantage from my point of view also that I do not need to specify the information structures, which could be very complicated. In fact, if you think about the Mertens and Samir state construction of an infinite hierarchy, is an exceedingly difficult object to work with.
Is there a unique information system if you have fixed base correlated equilibrium or not?
No. There might be many information structures which will all lead to a base Nash equilibrium which has the same distribution. Sorry, Al.
Could you contrast this with the non-Bayesian case where normally you think of correlated equilibria as being a larger set than Nash equilibria?
That's exactly right.
So why here are they somewhat the same?
Okay. So the intuition here, and that's good that you mentioned this, think about the complete information game. Okay? If I think about the complete information game, then we have a result which says that think about a Nash equilibrium. Okay? Think about the set of all Nash equilibria. That set might be smaller than the set of correlated equilibria. Okay? Why is that? Because when we look at complete information world, we do not, typically when we analyze Nash equilibria, we do not allow for correlation devices that the agents are using. You can think about correlated equilibrium as basically endowing the players or allowing them access to correlation devices. Now, I don't need to model them explicitly. I can simply think about it as information that I have about the other player. Okay? Once we take that point of view, then this equivalence result that I have here is also true for complete information game, and that's sort of a famous result by Brandenburg and Deckel.
So this result is applied when you're extremely agnostic about the nature of the information system, right? So for a lot of applications, the modeler assumes that there is some basic knowledge, like if you think of first price auctions as your motivating application with private values, then like a modeler might be willing to assume with confidence that everybody knows their own payoffs, but doesn't know, the modeler's not sure about how much each player knows about other players' payoffs. So are there sort of analogous results with an appropriate formulation of the correlated equilibrium for that kind of information?
Well, to begin with, I think to make this distinction is precisely sort of driving our interest. That is, one of the big problems actually in auction theory is how can you make the distinction between private values and common values, right? And to be able to infer that actually behavior is generated from a private rather than a common value interdependent auction. So I think that's one of the big open problems, and to make the assertion is far from obvious. Okay? What we are going to do here is to actually assume that the agents share a common prior on the payoff state. That is what we're going to fix. But what we do allow them to have is a multiplicity of private information about each other's information that is about the higher order beliefs. So in that sense, we're going to have some conditions on which you think makes this exercise interesting, because in some sense, we're fixing the payoff environment. If we're saying what is the social value of the game that we're analyzing, we know that, and we can determine that just on the basis of the utility functions and the distribution over the payoff element, the fundamentals of the game. Okay. Excellent. Okay. Good. So this is the first result. This is basically saying we can now with confidence just look at correlated equilibrium rather than Bayes Nash equilibrium, because we're using this epistemic insight about the relationship between Bayes Nash and correlated equilibrium. Okay. Mm-hmm.
Some of the correlated equilibria are extreme in the sense that I have to find very sort of obscure information structures to sustain them. I mean, I realize that the claim is that I can always be finding one.
Yes. It's a good question. Sort of think about this when I'm going to now go through the environment, and you will see that it has a very natural resolution in the environment that we're looking at, and presumably in others as well. Okay. Okay. So what's the environment that I want to look now? I want to look at environments with quadratic payoffs. Okay. That is where the utility of the agent is dependent on his own utility. On capital A, which I'm now going to take as simply the average actions of all the agents, and the type theta of the fundamental, the value of the fundamental variable. Okay. And so now I can think about the game basically as being completely specified by this interaction matrix gamma, which is basically just the matrix of the second derivatives, own and cross derivatives. Okay. Because it is a quadratic game, it's just dependent on my action and the average action of everybody else. It is also a potential game. Okay, that is the complete information version of this game, where we know what theta is a potential game. Okay. So think about this, rather abstract quadratic game. We can think about the gammas which just have a single subscript. It's basically the diagonal parameters. And the off-diagonals are basically the interaction parameters. That is, what's my sensitivity of my own action to the state, to the underlying state. How important, what's the interaction between the state theta and the average action. And what is the interaction between my action and the average action? That is basically what is the level of strategic complement versus substitutes. Okay, so that's, we're going to assume that gamma A theta is going to be different from 0 in the sense that my response, my payoff will depend on the underlying variable of the world. Okay, and we can categorize gamma A small a, capital A being larger than positive is basically an environment where we have strategic complements. If I increase my actions, or if my opponent increases his action, that increases my return, so my incentive to increase my action, or models of strategic substitutes. We're going to assume that gamma A is smaller than 0. That simply means that from the point of view of my own action, I have a concave utility function. Okay, that is the best response of each individual is well defined. And the concavity also prevails on the aggregate level. That is, we have interior equilibria rather than the non-existence of equilibria. Okay, this concavity at the aggregate level also means that, again, the complete information is not only potential game, but in fact it has a unique equilibrium. Okay, and more than that, actually, it is an example where not only the Nash equilibrium is unique, but where the correlated equilibrium is unique. And that's established in a very nice result by Niemann a few years ago. Mm-hmm.
So are the action spaces the whole real line?
So I'm going to look now at a continuum economy where basically, so I'll come to that, but where we have a continuum of agents, think about the unit interval, and the action space is basically the entire real line. Okay, and the state of the world, I'm going to specify this in a second, is also going to be the entire real line. Okay, so what are examples that sort of fall in this class of game? Think about sort of a version of the beauty contest where my utility is basically the weighted average between the distance between my action and the underlying state of the world. Is I have some interest in predicting the underlying state of the world, but I also want to be close in my action to what the other agents are doing. So that's sort of the coordination motif. Here it is not actually the case that both the mean and dispersion of the agent's action is going to matter, and that's a game which was sort of analyzed by Morris and Chin and then generalized by Angelettos and Pavan in 2007. Okay? Think about sort of another classic game, an oligopoly game, where we basically have a finite number of agents. Think about them as firms. What they have to choose is the quantity. The cost of production, say here, is quadratic. Then gamma A, the concavity parameter, is simply basically telling me what the marginal cost of the action is. The state of the world is simply what is the level of demand. And the inverse demand is going to identify what the price is as a function of the state of the demand and the supply into the market. Okay, this can all be rationalized by a representative consumer who has a quadratic utility function. Okay. We can also look at the continuum version where instead of having a finite number of agents, we have a continuum agent. This is sort of a competitive market with increasing marginal cost, and we can analyze that model as well. These are sort of just examples that you may want to keep in mind and think about when we do the analysis. Okay? Excellent. Okay. So the assumption that we're making now on the payoff environment is that the utility functions are quadratic, and that the underlying uncertainty, the uncertainty about the fundamentals, is normally distributed. These are the two assumptions that we're going to make. That is, the state theta has a normal distribution, which mean mu, and with a certain variance, which is sigma square theta. Okay? Okay. So now, just maybe to go back a little bit, or to emphasize the relationship between base, Nash equilibrium, and beliefs. Right? In this world, where we basically are uncertain about what the true state of the world theta is, you could imagine many information structures, okay, just to stay in the world of normally distributed signals. It could be the case that the agents all have access to some public signal about what the state of the world is. Okay. It could be that the agents have access to some private information, some idiosyncratic signal, again with a mean which is centered precisely at what the underlying state of the world is. That would be sort of public and private signals. But we can also push this further and say, well, not only as agent I do I get a private signal, I might also get a private signal about what the other agent's information is. Or I might have a signal about what the signal is that agent J got about agent K. Right? So you can easily see that we can sort of build a very rich model of strategic information on the basis of what I know about the underlying fundamentals, what I know about what agent J knows about the underlying fundamentals, and so on. That is basically what I meant early on when I meant to refer to higher order beliefs. Okay? And for every such information structure, I could compute the Bayesian-Nash equilibrium, some of them more realistic, others perhaps less realistic or more extreme. Okay? Okay? But I'm not going to do that. That is, I'm not going to make any further assumption on what the informational world is under which the agents live, but I'm rather going to say that I want to be able to say something about shared features that all equilibria have to possess independent of what their information structure is. And this little example should give you sort of an indication already, right? That basically by playing with the variables, in particular by playing with the variance of these variance signals observation, I can get a very rich parameterization, but I also get a parameterization which of course is going to be very hard to handle if I want to make a prediction for every possible information structure that the agent could have access to. Okay? Okay. And that's what I mean to say by the initial title, namely I promised you to give you ideas about what are predictions which are robust with respect to the information structure that the agents have access to. Okay? Okay. So now let's go to the notion of the correlated equilibrium. What is the correlated equilibrium in this world? It is simply going to be a distribution. Okay? It's going to be a multivariate distribution. Okay? And it's going to be a multivariate normal distribution, okay, which is going to be characterized by the mean of the individual action, the mean of the average action, and the variance covariance matrix between the state, the individual action, the state and the average action, and the individual and the average action. Okay? And so I can think about sigma capital A basically as sort of the aggregate volatility in the game, but how much is the average moving back and forth, and I can think about sigma small a square as basically sort of the cross-section. That is what's the dispersion of the individual actions in terms of their responsiveness to the state of the world. Okay? Right. And the one remaining assumption that I'm going to make today is that I'm going to focus on symmetric equilibria, which is sort of a reasonable thing to do when you think about the continuum in some sense of exchangeable agents. Okay? In which I will gather some additional information in the sense that now it must be the case that the average action is exactly the mean of the individual action, okay? And that when I look at the variance covariance matrix, the correlation between my action and somebody else's action, which is basically captured by the correlation coefficient rho a, is also going to be the correlation between me and the average action. Okay? So that basically a correlated equilibrium can now be characterized by the distribution of the actions, mu a. I dropped the subscript here. And by the endogenous element of the variance covariance matrix, which is sigma a, and rho a theta. Okay? So basically by the variance and by the correlation coefficients across the actions and the correlation coefficient between actions and the underlying state of the world. Okay? So now, the one advantage I get when I look at quadratic games is that, of course, the best response functions are going to be linear. Okay, that is, I can now just look at a linear best response function. What I will find is that my action, okay, in any correlated equilibrium, has to satisfy the following relationship. It must match with the weighting parameters given by the interaction parameters reflecting the sensitivity that I have to the state of the world and to the actions of the other. It must match the weighted sum or a convex combination between my expectation about what the underlying state of the world is, okay, and my expectation what the average actions of the players is in this game. Okay? That is, I now basically just have one equilibrium condition, okay, which uses the fact that conditional on my own action, I have some information, I can extract some information on what the other agent's actions are and what the underlying state of the world is. Okay? Okay. And so now, think about this. Basically, since this has to be true for every action that I'm taking, and I drop the subscript I now because I can think about the representative agent, I basically say now that this equation has to hold for all A. I basically give a first order condition which has to be constant equal to 0 or equal to 1, because we're going to differentiate with respect to A, across all possible recommendation or across all possible action that an agent can take. So that's going to give me some conditions on what the relationship between the individual action, the average action, and the correlation between state and the individual action is. Okay? But this is sort of a property which has to hold for every A. In particular, it has to therefore hold in expectations across all A. So that's sort of a summing up constraint, a flow constraint that has to be satisfied for all correlated equilibria. Okay? And so this first insight, namely that it must be true that this condition is true for all in expectation, means that I can rewrite this in terms of the expected value that A is going to take. And what you find then on the right-hand side is also the expected value of capital A, which in this model has to be also the expected value of A. So that gives me already the first result. That is, irrespective of the information structure, it must be the case that the mean of the individual action, okay, the mean outcome of the individual action is fixed and precisely identified by the interaction matrix. Okay, that is, we have a unique. There's an I on the left.
It says AI, and then
It should just be A, right?
It doesn't matter. But I guess what I wanted to emphasize is that we're talking about the action of the individual agents. Okay, on the right-hand side, there is no I, because that is simply the representative interaction matrix. Okay, what are the variables which enter on the right-hand side? They're just the mean of the state variable, which is mu, and then the interaction parameters, that is the amount in which there is a strategic substitute versus complements, and the extent to which the fundamentals matter, that is to the degree to which I'm sensitive to the realized state of the world. You want to go back?
this is just the expectation of that equation.
This is just the expectation of this equation of all possible realization of A. Right? And then solving for the fixed point, saying small a must be equal to capital A. Okay? And in fact, because it's this expectation operation, this result is actually independent of either the symmetry argument or the normal distribution. That is true irrespective. That is true for all quadratic payoff utility functions, but we don't need symmetry, nor do we need normal distributions.
I thought we used symmetry to get the expectation of big A was the expectation of little.
What I can say that the average actions of the across all individuals must now satisfy that if I don't assume symmetry. Yes.
And didn't you use that it was a quadratic game?
No, and I used the quadraticness, but I do not use to refer the distributional properties here. Okay. Where I'm going to use now the distributional properties when I'm thinking.
No, because the parameters gamma, that's
Those are known parameters. These are exogenous parameters about the strength of the interaction. Yes? Okay. Where I'm going to use the property of the normal distribution is precisely now in the updating process. Okay. And in the observation that from this best response function, this best response function has to hold for all A, I'm getting a tight condition on what the relationship has to be between the covariance elements. Okay. So now looking at the covariance, we just need to determine the standard deviation and the correlation coefficients. Okay. And the description that we get from the correlated equilibrium is to say that a triple, in terms of the variance and correlation coefficients, form a base correlated equilibrium if and only if we satisfy the first inequality, namely that the correlation of action is at least as large as the square of the correlation between action and the underlying state variable. Okay. And given that we have this inequality, then we can use the best response property to actually exactly determine what the standard deviation of the action has to be. Okay. Okay. So I have until.
Oh, we're fine. Another 20 minutes.
Exactly. Okay, great, wonderful, good. So here's just a visual representation, which we'll come to back in a second, about what the set of correlated equilibria look like. Okay. It is, and now just in terms of the correlation coefficient, we can infer or back out what the what the underlying variance is going to be. Okay, so it's clearly is now not a unique prediction anymore. Right? That's different from the world that we had when we had complete information. Then base Nash and correlated equilibrium is unique. That's not going to be the case here. Here we have an entire set of possible correlated equilibria. Okay. We can then sort of think about comparative statics and see what the properties of these games are, in particular how the correlation coefficients and the variance move as a function of the structure of the game, namely whether we have strategic complements and strategic substitutes. But let me now actually go back and spend a little bit more time about the relationship between the base Nash equilibrium and the information structure and the base correlated equilibrium. Okay. Okay. So we had this general result between in terms of the equivalence, but now of course we may want to ask what do base Nash equilibria in particular, what would information structure would have to look like in order to generate the correlated equilibria, and is there a sense in which we can say what kind of information structures can actually support the base Nash equilibrium or the base correlated equilibria. Okay, and it turns out that actually the entire set of base correlated equilibria can be generated. Okay. By basically by bivariate information structure, which simply gives all the agents a public signal, okay, which is S, which they share, that it is common to them, and then a private signal, which is the idiosyncratic signal Si. Okay, and where in this large space you are is then uniquely identified by the standard deviation, basically by the informativeness, by the precision of the public signal and the private signal. Okay. In terms of the uniqueness, it's going to be true that there are other information structures which would generate a similar distribution, but in fact just this parameterization, this bivariate parameterization between public and private signal is enough to give you the entire set of correlated equilibria.
When you do the big epistemic proof, the major proposition, are you going to prove it in exactly this way?
So this is true for all quadratic games, but it's not. It's going to certainly not be true for all games. Okay. Okay. So that's basically statement. We can find a base correlated equilibrium, which is now just characterized by the correlation coefficient, if and only if we can find a precision or a variance of the public and the private signal, and indeed that exhausts the characterization. Okay. Very good. Okay. Let me just focus now on two aspects. So I'm gonna skip that. One interesting aspect, I'm just going to give you sort of the idea. One interesting aspect of this characterization is that now we could ask, since we have characterized the entire set of correlated equilibria, and we know that this is exhaustively characterized in terms of the variance of the private and the public signal, we could ask what kind of information structure is the information structure which maximizes the social welfare in the game. Okay. That's now a well-posed question, and with this equivalence result, we know that we basically know what is the space of information structures over which we have to solve or characterize this problem. Okay? And this actually gives some interesting new insights to a large literature, which is sort of very nicely summarized in work by Wright and Vivas on information sharing in oligopoly, where the question was, is it socially beneficial for firms to share information about common cost or common demand parameters? Okay? And what we can show here is that actually typically the socially beneficial arrangement will be that all the information is shared. And interestingly, from the point of view of industry profits, it is typically going to be the case that partial information sharing, that is some kind of private information, noisy information, is optimal to maximize the industry profit. And that's basically because the agents are going to play off dispersion in terms of supply with the information, with the benefits from more information. which is something which did escape the early literature completely because they could just think about complete versus sort of complete information versus zero information. Here we have now a framework in which we can think about interior information structures. Okay. Let me talk about identification, and then let me talk a little bit about additional information, or what are the restrictions that we can impose when we have additional information. Okay. Here, the first part of the talk, we talked just about prediction. Let me now just emphasize that we could now reverse it and say, well, given that we assume less about what the information structure is, can we still identify, that is, think about ideal conditions under which a statistician from the observed quantities could make inferences about the nature of the structure problem. Okay. And interestingly now, in the Bayes-Nash equilibrium, for any given information structure, we can actually identify, that is, we can exactly identify the interaction parameters which are so typically of interest, namely whether they're fundamentals methods in a positive or negative way, whether they're positive or negative externalities, and also whether they are positive or negative interaction parameters. Okay? The interesting aspect is that as soon as we do not make very strong assumption about what the information, the strategic information of the agent is, we are also losing some amount of identification. That is, we will be able to still identify the sign of the interaction between the agent's action and the underlying variable, but we cannot identify anymore whether actually the agents play a game with strategic complements or substitutes. Okay? That's sort of striking in a sense, because you would think this is sort of an elementary property of the game which you should infer and back out from the data, but with weaker informational assumption, and in our view sort of more realistic informational assumption, we will actually not be able to back this out of the data anymore, even under ideal statistical conditions, that is large sample and so on. Okay. And then the second aspect, which is a little bit related, is to the question, well, clearly, perhaps to some of you, we made still sort of a too weak assumption about the information that the agents have access to. That is, we could ask, well, maybe we don't know precisely what the agent's information is, but maybe we can give some lower bounds. That is, maybe it is the case that from past data we can infer that the agent have at least access to a common signal with a particular precision sigma s, or that the agent have at least access to some private information with some variance or some precision sigma I. Okay? And it's then natural to ask, is given that that is the nature of the lower bound, what are the further implications, or what are the additional restrictions that we get from lower bounds on the nature of the equilibrium? Okay. Right. And if you now sort of just try to generalize what the notion of the equilibrium condition is, the correlated equilibrium condition, then it must be the case that my best response is established with respect to a conditioning which is not only with respect to my own action, but also with respect to that public signal, at least that, and with respect at least to that private signal. Okay, that means that my action, the first order condition, should be invariant with respect to all public signals and all private signals. Okay? In other words, we get now a new set of equalities in terms of the nature of the best response function, and we can turn these equalities into conditions on the moments, on additional conditions on the moments. Okay? And in the correlated equilibrium, it is basically to say that now we have further restriction, that is the correlation coefficient, say rho A and rho A theta, doesn't need to be larger than 0, but it needs to be large enough to even be larger than 0 after we took account of the minimal correlation between action and the public signal, or between action and the private signal. Okay? And so this inequalities then basically give result to sort of refinement in the set of correlated equilibria that obtain. That is, if before we were thinking about the correlation coefficient, the relationship between rho A and rho A theta squared, right now I'm taking rho A theta squared, so that basically the entire set of correlated equilibria is the entire set which is in the unit cube or in the unit square under the 45-degree line, right? Then I can say, well, what kind of behavior can I eliminate after I have noticed that they have at least access to that much information. Okay, so what we have here, sorry that it got cut off, is a description of what the precision is of the public signal that all agents have access to. Okay, so that as agents have access to a more and more informative signal, what will happen is that there must be more correlation among the actions, and there must be also more correlation between the action and the underlying state of the world. Okay, so that is the equilibrium prediction becomes now sharper if we have a stronger bound on what the information is that agents have at least minimal access to. That it's in some sense reducing the information structures that we have to think about. Okay, and sort of a final point in terms of application. So this is a characterization of how the equilibrium set looks, and it's basically just a formal statement of the geometry that you saw, namely that the sets are shrinking and that they're nested, okay, and that in particular the correlation between the actions and the correlation between actions and states is uniformly increasing. That is at least the lower bound of that is. Okay, and we can do the same thing for the private information. Okay, so let me just give you sort of one way in which I would now use sort of the robust consideration to make robust predictions also for games. So think about robust policies which do not depend on a specific informational assumption, but is valid for all informational assumption. Okay, this is sort of a analysis which is interesting in the context of beauty contest, where the question was: is there value to public information, or is there value to private information? And was also pursued by Angeletti and Pavan in the context of optimal taxation in sort of in this quadratic games. Okay, and I just want to think about here robust informational policy. Okay, in the beauty contest, that is one of the examples that we discussed before. What we saw is that because the agents basically are interested in coordinating both with respect to the state and with respect to the average action, they will often follow a public signal, not because it's particularly informative, but because it allows them to coordinate the actions with the other agents. Okay? And from a social point of view, it might actually be desirable to have just coordination in terms of making good predictions, but not put so much weight on the coordination among the agents. Okay? So Morich and Shin observed, because of this attention between the individual action and the social value of action, it is the case that in some instances, or in many instances, public information, strangely enough, has socially negative value because it leads the agent to just coordinate on their actions and to basically disregard or in fact put less than optimal weight on their private information. Okay? So this, for a given private information, it is going to be the case that I would like to reduce the public information, the precision of the public signals. Okay? Now, in a robust world, we may want to ask, is that really true? That is, suppose we don't know exactly what the level of private information is, and suppose that we don't know exactly what the level of public information is. Is it the case that if we increase the public information, the social welfare is decreasing? Okay? Across all possible information structure that the agents may have. Right? Rather than looking just at one, we're now simply saying, well, let's take the least favorable instance of that, and let's say whether public information is increasing the value of the least favorable instance. So in some sense, we're solving now a robust version of the problem.
So are you asking the question whether the meat market is sort of socially beneficial or not?
In Boston? Where?
No, the meat market for economists.
I think let's talk about the central bank and the ability of the central bank to provide information. Yes?
Right? So
yes, so this is a perfect example.
Somebody and you have some private information, but then other people act.
I'm going to talk to my colleagues at Cambridge, and they're telling me, oh, this guy just interviewed marvelously, and coming back from a little town near Haven, I'm saying, well, these guys certainly must know, and I should disregard my own information from my own interview and say, well, they made an offer already, I might as well make an offer as well. Okay, and the insight that Morris and Shin has that in many situations it can actually be socially inefficient to basically provide public information because it allows me to coordinate and to disregard or put less than socially efficient weight on my own private information. Okay? The argument that we're pursuing here is to say, well, that's only true for specific information structure. If I want to make this argument robust, it's actually not going to be true. That is the robust version. It's always true that more public information is at least weakly increasing the social value of the problem. Okay, because the minimum instance is always going to be, in some sense, determined by the situation when we have so little private information that actually an increment in the public information is socially useful. And so therefore, when we come to sort of a robust version of this evaluation, we'll find that actually the exact and the robust policy have quite different in nature.
Mm-hmm. The intuition for this, what you showed in the picture, that if you provide more information, then you're shrinking the set so that the minimum...
You're shrinking the set, but in particular it happens that the minimum in terms of where the social welfare is minimized, that minimum is actually increasing. If I just look at the point and I shrink the point, then that's not necessarily the case, but if I look at the entire set and I look at the minimum with respect to that set, then it's increasing. That's exactly right. Okay. And I think with these sort of two sort of applications or sort of further direction that one could pursue, I'm going to leave it today and basically hope to have convinced you that we can actually in many environments make quite interesting, quite meaningful, robust predictions, even if we don't have very strong, make very strong assumptions to strategic information, but there's going to be a loss. And one loss that we saw is that instead of being able to identify the parameters, we're only going to be able to partially identify them. And of course, that might be interesting not only sort of from the theoretical point of view, but also if you think about pursuing empirics, that is, what can you learn from the data if you don't want to make very strong assumptions about the informational hypothesis that you entertain about the behaviors of the agents. Okay. Excellent.
About this idea of a robust information policy. So when I think about some robust mechanism design, I think of sort of guaranteeing that I can achieve some properties which sort of is attractive. It doesn't seem quite as attractive to design policies on the basis of what would be robustly welfare improving. So in the worst, it doesn't seem as attractive to design policies on the basis of what would be robustly welfare improving. So releasing information is best in the worst case, but you know, perhaps in the average case it's a terrible idea, right?
Yes.
And it doesn't. It's got the, you know, you're sticking the same word robust in front of it, but in the one case it really seems like sort of the idea of robust mechanism design seems like it's definitely a good thing. If you can guarantee me this, that's great.
Mm-hmm.
It doesn't have that sort of guarantee feel to it. It just has a, I guarantee something in the worst case. Why?
Well, you know, in the robust mechanism design world, we were fortunate enough to be able to make arguments which were completely distribution free, right? That will not be the case in all or in many circumstances which are of interest. What I try to argue here is that we can actually still learn quite a bit from making minimal assumptions about the information environment, in particular playing off the distinction between what is sort of payoff relevant and what is sort of strategic information, which typically from revealed preference arguments I might learn much less. Okay, but you're right that once I think about uncertainty, there's a question of how much weight do I put on sort of the lowest one as opposed to any other events. I guess one of the ways in which we're thinking about is that now we could also make an argument, right? So now that we know in some sense what are the information structures which are generating this equilibria, we could now of course think about taking then again a much more Bayesian point of view and say, well, let us impose a prior on how likely we think these information structures are, and say, when is it the case that what kind of concentration or what kind of distribution on the information system would we need to assume in order to make this robust insight, which was just an insight at the minimum, valid for all distributions or at expectations at least. And so given, you know, sort of the flexibility of this quadratic normal payoff, that's certainly something one could do and one might not have expected that one would be able to do. So that's definitely a point which is interesting. Yeah, thank you.